Problem sheet 7, question 3. A burger truck has been contracted to supply burgers for a music festival. The festival is to last 5 days, however the burger truck only has 3 boxes of frozen meat, and once defrosted, each box of frozen meat only lasts 1 day. It costs €1,000 per box per day to keep frozen. The burger truck must decide how many boxes to defrost and sell each day of the festival. They anticipate that they will take in €1,500 per day if they defrost 1 box, €3,000 if they defrost 2 boxes on the same day, and €3,500 if they defrost 3 boxes on the same day. However, due to a broken contract, they will incur a fine of €2,000 each day they do not offer burgers. Use dynamic programming to devise a strategy that will maximise the burger truck's intake. So remember, for dynamic programming, we need to do 3 things. First, we need to formulate the problem as a directed acyclic graph. Then we want to order the nodes. And we want to do that in such a way that when we analyse one node, we've already analysed all its descendants. Third, perform value iteration. And then finally, we're going to read off that solution. So first we want to formulate this as a directed acyclic graph, but it doesn't immediately look like a problem on a graph. So we are going to look for a way to represent the state of the system as nodes, and edges are going to represent ways that we can transition from one state to another. They could be actions. So what are the important information about the state of the system? So if I turn up to the burger truck and I ask them what's going on, they will immediately say it is day 2 of the festival and I have 3 boxes of meat left. So the important information is what day of the festival it is and how many boxes of meat they have left. So we're going to let the tuple Tn denote the state of the truck. Where T is going to be the day of the festival and N will be the number of boxes of meat left frozen. Now let's have a think, what possible states could the truck be in? Well, T, the day of the festival has 3 days. So we can be at the start of the festival, day 0, where we know we have 3 boxes left, day 1, day 2, and day 3. N then is the number of boxes. We could have 3 boxes, we could have 2 boxes, 1 box, or 0 boxes. There's no other options. So now we can write down all possible states that we could be in. So we could be in state 03. That is, at day 0, which is right at the start of the festival, before we start, we have 3 boxes frozen. At the first day of the festival, we could defrost nothing. We'll still have 3 frozen boxes. Or we could defrost 1 box and have 2 left. Default 2 boxes and have 1 left. Or defrost all 3 boxes. And we can take actions from state 03 to reach each of these. On the next day of the festival, again, we could still have 3 boxes left. Could have 2 boxes left, 1 box left, or 0 boxes left. Can we reach each of these? Yes, well, if we were in state 13, so yesterday, if we had 3 boxes left, we could defrost nothing and get to state 23. We could defrost 1 box, 2 boxes, or 3 boxes. If we are in state 12 and we only have 2 boxes defrosted yesterday, we cannot get to state 23. We can't gain a box frozen, but we can defrost nothing, defrost 1 box, defrost 2 box. If we're in state 11, again, we cannot gain a box, but we can defrost nothing to get to 21, or defrost 1 box and get to 20. And if we have 0 boxes on day 1, then the only thing we can do is have 0 boxes on day 2. Similarly then, for day 3, we could end up with 3 boxes, 2 boxes, 1 box, or 0 boxes. And we do have actions that we can take to all three of those. So when we have 3 boxes, we can defrost any amount and get to any state. When we have 2 boxes, we can defrost any amount and get to any state, 2, 1 or 0. When we only have 1 box, and if we have 0 boxes, we can only get to this state. We can do the same for days 4 and finally day 5. And this would be the structure of our directed acyclic graph. Now this structure is useful. It tells us intuitively when we're in a particular state, what actions we can take and what state we would end up in by taking those actions. So for example, if we are in state 2-2, the actions we can take are defrost nothing, defrost 1 box, defrost 2 boxes. Now we need a reward for every action. And what is the reward that we will get for every action? Let's consider one action isolated at the moment. Let's just consider this action here. This is the action of going from state 2-2. So on day 2, we have 2 boxes frozen. We defrost 1 box. And so on day 3, there's only 1 box left frozen. We have defrosted 1 box. And so we anticipate we'll make €1,500 that day. On this day, we have 1 box to keep frozen, and it costs €1,000 per day per box to keep frozen. So we are keeping 1 box frozen on that day, so that would be minus €1,000. And we have not incurred any fines. So that would result in a reward of half or €500. Let's have a look at another action. For example, this action here. I start off in state 1-3 and I end up in state 2-3. What reward will I get here? So I have defrosted 0 boxes, so I will get no money at all from selling burgers. I am keeping 3 boxes frozen, and it cost me €1,000 per day to keep those boxes frozen. So it will cost me 3 times €1,000 per day to keep those boxes frozen. I don't sell any burgers, so I don't make any money. But I've also not offered any burgers, and that is a broken contract. And so I will incur a fine of €2,000 for every day I do not offer burgers. So I would also incur a fine of €2,000, so that would be a reward of minus €5,000. So rather than write down on the directed acyclic graph what the reward is each time, we can work out what the reward is based on the action we take, the state we started in, and the state we end up in. So let's work that out as we go along during our value iteration. Our second step of dynamic programming was to order the nodes in such the way that when I analyse them, I have analysed all its descendants before itself. Now there is a natural ordering to the state here as there is a time element. I cannot analyse any day 4 states if I have not already analysed day 5 states, as all day 5 states are descendants of all day 4 states. Within a day, no state is a descendant of each other, and so what we will do is just analyse all of each day's state in turn. So we'll start off by analysing all of day 5 states, because they have no descendants, then all of day 4 states, as they only have day 5 states as descendants. Then we will analyse all day 3 states, as they have day 4 and 5 states as descendants. Then we will analyse all day 2 states, as they have day 3, 4 and 5 states as their descendants. Then we will analyse all day 1 states. Then we will analyse day 0 state. Now we will begin the value iteration algorithm. So we'll set up our table. So we'll have to start off with what state are we leaving from. Then after taking a particular action, which is how many boxes we'll defrost, we'll end up in another state. What is the reward for taking that action? We can work that out. What would be the reward plus the value of the state we end up in? and therefore what is the value of our current state. So we said we're going to start off with all day 5 states, and there's nowhere to go for these. So we can start off with state 5.3, there's nothing to do, we end up going nowhere, we get a reward of 0, and so a value of 0. Similarly for all other states on day 5. That means we have analysed all the following states. Now we can move on to day 4 to analyse state 4.3. Now what can we do here? There are actions we can take. We can either defrost 0 and end up in state 5.3. We could defrost 1 and end up in state 5.2. Defrost 2 and end up in state 5.1. Defrost 3 and end up in state 5.0. That's all the actions we can take here. What would the reward for each of these be? So if we defrost 0, then we are not selling burgers on that day, so we will get a fine of €2,000. Plus we are keeping 3 boxes frozen, that'll be €3,000, so this will be a fine of -5. -5 plus the 0, which is the value of 5.3, where we end up in, is -5. If we defrost 1 box and end up in state 5.2, we do not incur the fine. We estimate that we will make €1,500, so that's 1.5. But we need to keep 2 boxes frozen. That's going to cost us €2,000. So this is going to cost us minus 0.5. We'll end up in state 5.2, which has a value of 0. If we defrost 2 boxes, again, there is no fine. We estimate we will make €3,000. We're only keeping 1 box frozen, costing €1,000, and so we will make €2,000. We will end up in state 5.1 with a value of 0. If we defrost all 3 boxes, then we estimate that we will make €3,500. There is no fine and no cost for keeping any boxes frozen. Out of these actions, the best action would be to defrost all 3 boxes, and so the value of 4.3 will be 3.5. Now let's look at state 4.2. What can we do here? We can defrost 0, 1, or 2 this time, and end up in states 5.2, 5.1, and 5.0. If we defrost nothing, then we will incur a fine of 2,000, and we're also keeping 2 boxes frozen at a cost of 1,000 each, so this will cost us minus 4,000. We will end up in state 5.2, which has a value of 0. If we defrost 1 box, we estimate we will make 1,500, but we need to keep 1 box frozen at a cost of 1,000, so overall that would be a reward of 0.5,000. And if we defrost both boxes, then we estimate we will make 3,000. There is no fines and no boxes to keep frozen. So the best action to do if we're in state 4.2 is defrost both boxes. How about state 4.1? We can either defrost 0 boxes or 1 box. Ended up in states 5.1 or 5.0. Defrosting 0 boxes, we will incur a fine of 2,000 for not selling any burgers, and we have to pay to keep 1 box frozen, which will cost 1,000. So this will overall be minus 3,000. If we defrost 1 box, we estimate that we will make 1,500. We don't have to pay to keep any boxes frozen, so we will estimate we will get a reward of 1,500. Out of these, if we're in state 4.1, the best action to take is to defrost 1 box. And finally, we can look at state 4.0. There's only 1 action we can take here, which is to not defrost anything because we don't have any boxes. This will take us to state 5.0 with reward minus 2,000 for the fine of not providing any burgers, but we have nothing to keep frozen. Okay, that seemed a lot of work and we have a lot more states to do, but think about it now. For all states in day 3, the reward pattern will be exactly the same, because it didn't really matter what day we were on. That didn't affect our rewards. The only thing that affected our rewards was how many boxes we started with, how many boxes we defrost in, and how many boxes we end up with. State 3 will have exactly the same rewards. We will just be going, instead of from 4-3 to 5-3, we'll be going from 3-3 to 4-3 and so on. So this should be fairly easy to start filling in now. So let's go do that. Now what will change will be the next column, because instead of going from 4-3 to 5-3, where 5-3 had a certain value, we are now going from 3-3 to 4-3, and 4-3 has a different value that we've already calculated. That's 3.5 on the screen. So here, going from 3-3 to 4-3, defrosting 0 boxes. Defrosting 0 boxes, the action will give us a reward of -5, but ending up in state 4-3 will give us a value of 3.5. Similarly for the rest, going to state 4-2, the action will give us a reward of -0.5, but we end up in state 4-2, which has a value of 3. Now the largest value there is 2 plus 1.5, giving a value of 3.5. Okay, we can repeat this process now for the day 2 states. Now in this case we actually have a tie. Both minus 0.5 plus 2 and 2 minus 0.5 both give us a reward of 1.5, which is better than any other value there. So the state 2-3 does indeed have a value of 1.5, but there were 2 ways of getting there, either by defrosting 1 or by defrosting 2 boxes. And now the same for all the day 1 states. And again we have a tie, so both defrosting 1 and 2 boxes will give this a value of minus 0.5, which is the best we can do here. And finally, we can analyze the day 0 state. which completes the algorithm. Now all we need to do is read off the solution. But that's going to be a little bit more difficult here because we have ties. There's a few places where we have ties. So what I'm going to do first is highlight all the optimal actions. So in this case, 0, 3, the optimal actions are both defrosting 1 and 2. Another tie there. Another tie there. And so I've highlighted all the possible optimal actions. How does that correspond with paths through this directed acyclic graph? Well, each edge is an action, so let me highlight all the optimal actions. So I've highlighted all the possible optimal actions. Now we know that any actions that are not optimal will not be taken. So those are actions that we can remove. Okay, so this leaves the same directed acyclic graph, but only leaving in the optimal actions. You'll see that there are some states, for example 5,3, 5,2 and 5,1, which are not reachable via any optimal action, and so we can remove those. Now also remember that we always start at time 0, and so in state 0, 3. So from here, following optimal actions only, there are still some states that are completely unreachable. So for example, 1, 0 is unreachable, 1, 3 is unreachable, 2, 3, 3, 3, 4, 3, 4, 2 is unreachable, 2, 2, 3, 2, 4, 1 is unreachable. And so these can be removed as well as any optimal actions emanating from those. And that leaves this graph here, where we have two distinct paths from our starting state 0, 3 to the end, where we end up in state 5, 0. What do those paths correspond to? So the first path, the uppermost path, would correspond to defrost 2 on the first day, defrost 1 on the second day, and defrost 0 forevermore. The second path would correspond to defrost 1 on the first day, 1 on the second day, 1 on the third day, and 0 forevermore. So therefore, our optimal solutions are defrost 2, 1, 0, 0, 0, or 1, 1, 1, 0, 0.